Welcome back everyone. In this lecture we will complete the proof of this structure theorem of finite abelian groups. So let us actually start with some preparatory results. So let as before G be a finite abelian group. I will split the proof into some small facts. Okay. So let us start with first fact 1. So it says if you have two subgroups, let's say H and K, or subgroups of G, such that the order of H and order of K, they are relatively prime. The GCD of order of H and order of K, if this is 1, so then the H intersection K must be trivial. Okay. So why this is true? So let us start with X inside our H intersection K. So then what we know from Lagrange's theorem, that order of H must divide order of H intersection K. But since H intersection K is a subgroup, okay, H intersection K is a subgroup of H as well as K. Again using Lagrange's theorem, you can see that. So using by Lagrange's theorem, you can see that order of H intersection K divides R of H and R of K. So that means this order of X divides order of H and order of K. So then what will happen, because they don't have anything common, so the GCD of order of H and order of K is 1. So that forces that this order of X must be 1. So order of X must be 1. So that will imply X is identity. So this proves that H intersection K must be identity. So now let us look at how one can use if you have subgroups whose intersection is identity. So here is fact 2. So let H and K both are subgroups of G, and G is fixed to be finite abelian group, such that H intersection K is, let's say, identity. So now what one can do, one can define this natural homomorphism from H cross K to G. Okay, there is this phi. You can define the homomorphism from H cross K to G as follows. What is a phi of H comma K map to, which is equal to the product HK. Okay. Now since G is abelian, one can check that this map must be homomorphism. Now since H intersection K is identity, this must be actually injective homomorphism. So I will leave it to you to check this is indeed homomorphism. So let me check it is injective. Suppose Hk is same as H dash K dash, then that would imply that H dash inverse H is equal to K dash times K inverse, but which will be inside H intersection K, because this is in H and this is in K. So that forces that both these elements are identity, that forces that H equal to H dash and K dash equal to K. So this proves this phi is indeed injective homomorphism. Injective homomorphism. So now in case if you assume that okay, so this is a immediate corollary. In case if you know that the cardinality of G is same as the cardinality of H times cardinality of K, so then G must be isomorphic to H cross K. So that is because this map must be any injective map from one set to another set, both are having same cardinality, must be bijective map. So, this phi becomes bijective, so it becomes isomorphism. So, that is immediate corollary from this. Okay. Now, let us reprove Sylow's theorem in this setting. Okay. You have this finite abelian group of order n, and let us say P divides n. So, where n is your order of G, and G is given to be finite abelian group. So, what we want Sylow P subgroup. Okay, what is the property of Sylow P subgroup? Let us say P power E is the highest exponent that actually divides R of G. So, E is the maximum exponent such that P power E divides order of G. So, that means P power E plus 1 does not divide R of G. Okay. So, then Sylow's theorem guarantees that there is a subgroup of order P power E. Now, if you think about it, you can actually give this characterization for that subgroup. So, this is those elements x in G such that this order of x indeed is a power of this prime power P is a power of P. So, including like trivial power P power 0 is also allowed. So, that means order of x equal to some P power alpha where alpha greater or equal to 0. So, that is what we say. So, if you take Sylow group subgroup, then you can see that Sylow subgroup, all the elements of the Sylow subgroup must satisfy this property. Okay. But in this case one can define this, there is no issue that H being a subset of G such that those elements such that R of x is a prime power P power alpha for alpha greater than or equal to 0. So, now what we claim in this case, this is the Sylow P subgroup. Indeed, H is a subgroup of G and this H must have cardinality P power E. So, these two things we will actually verify in this case. Okay. So, maybe it is more intuitive to call this H as G of P. So, let us call it G of P because depending upon the prime P. So, G of P is a subgroup and the cardinality of G of P is P power E. That is what we want to prove. So, let us see how one can prove. So, proving it is a subgroup is easy. Start with two elements x, y in G of P. So, then look at the order of x, it is going to be some P power alpha, order of y is going to be P power beta. So, then order of y is same as order of y inverse. So, that is what it is going to be P power beta. So, now if you look at x y inverse power P power alpha plus beta. So, then you are going to get exactly x power P power alpha plus beta times y inverse power P power alpha plus beta, and both alpha plus beta is going to be greater than or equal to both alpha and beta. Okay. So, that means this is identity and this is also identity, this is going to be identity. So, this proves x y inverse order also must be some P power gamma for gamma greater than or equal to 0. So, this proves x y inverse is in G of P and G of P is indeed a subgroup of G. Now, we want to say that G of P must be having some prime power P power E exactly for that exponent E. Okay. So, this is the exponent, highest exponent of this prime power P. So, why that is the case? So, first of all, we claim that the order of G power P must be some P power gamma, okay, for some gamma. Again gamma has to be less than or equal to E. Why that is the case? Because if some other prime divides this, let us say Q, say Q is some other prime divides the cardinality of G power P. So then what happens? Using Cauchy's theorem, again Cauchy's theorem we verified it for finite abelian groups. What it says, if some prime number divides the order of the group, then there exists an element x in this G of P such that order of x equal to Q, but which is not of the prime power, because this by description of G of P, all elements must have some P power some gamma dash. But this is a contradiction because Q and P are distinct primes. Okay, so P is not equal to Q, which is a contradiction. So that forces that there is no other prime that divides this cardinality of G of P. So that means the cardinality of G of P must be this that particular prime P power something. And since G of P is a subgroup of G, so the cardinality of G of P must divide the cardinality of G. So that forces that this P power gamma divides the cardinality of G. So that forces that gamma must be at most E. So this is immediate from Cauchy's theorem. So now again we will use Cauchy's theorem to ensure that gamma must be equal to E. So let us say gamma is strictly less than E. Okay. So then what we can do, I can go modulo this G of P. Since G is abelian, any subgroup is normal. So G of P is a normal subgroup of G. So I can take this G modulo G of P. Now note that the cardinality of this has to be P power E minus gamma times something. Okay, call it A. E minus gamma must be greater than or equal to 1 by our assumption. So now again we can use Cauchy's theorem. So what Cauchy's theorem says, since P divides G modulo G power P order, that implies there exists an element x G of P inside G modulo G power P such that the order of x G of P is exactly equal to P. But what does it mean? This means x power P must be element of G of P. Okay, because x G power P is a coset. So it has order P means x power P must be having this must be element of G of P. So now if you take x power P power P power gamma, okay, so that is going to be exactly equal to x power P power gamma plus 1. So this must be identity. Okay, because the cardinality of GP is exactly P power gamma. So any element of that G power P, if you raise it power the cardinality of G of P, that must be identity. So in particularly this says the order of x must be P power something. Okay, so that means x is inside G of P by definition of G of P. G of P, those elements in G such that order of G is prime power P power alpha, alpha greater than or equal to 0. Okay. So since this R of x is of this form P power star for some star greater than or equal to 0, so that forces x is in G of P. That means xgp is trivial. Okay, that means xgp is gp, but we by our choice this xgp having order p which is also a trivial element, which is a contradiction. So that says that this G of P must have order P power E. So that means this G of P is our silo P group. Okay. So the existence of silo P group is somewhat trivial. Once you know the Cauchy's theorem, then we will be able to produce this existence of silo P group in the finite abelian group. That is because we are allowed to go modulo any subgroup, there is no issue. Okay. So you can actually think about proving this Solo's theorems for the finite abelian groups without much trouble. Okay. The proof that we used uses this group action, but now knowing that you can go modulo any subgroup because all the subgroups are normal, somewhat reduces your argument via induction. Okay. So now using induction on the finite abelian groups, any quotient of finite abelian group is going to be again finite abelian group. Using all those information, you can actually write down some somewhat simpler proof for the Solo's theorems in the case of abelian groups. Okay. Indeed, that's what we have done here, but I am just emphasizing that. Okay. Now, if you take these various primes, okay, let us say the cardinality of G is n, which is P1 power E1 etc. PR power ER. So then what happens if you look at this G of P1 cross etc. cross G of PR. So this is going to sit inside your G. Okay. So this is naturally follows from the fact that we proved earlier. So what is the fact that we proved? If you have H and K such that H intersection K is identity, then there is a natural injective homomorphism from H cross K to G. And not only that, if you have a HK both having relatively prime order, then H intersection K must be identity. So this says that if you take this G of Pi and then look at all other product, okay, look at G of Pi and then intersection with those all other G of Pj, j not equal to I. So this will be a subgroup because we are in the abelian case, we don't need to worry about taking the product. So if you take these two subgroups, then the intersection must be trivial because this has order Pi power Ei and this has order product Pj power Ej where j not equal to I. So that means they have relatively prime orders. So that means intersection should be identity. And since it is true for all I from 1 to R, so if you look at this Cartesian product or the direct product of this these subgroups, then that must live inside G injectively. Now since G has same order as this P1, E1 etc. PR, ER, that forces that G must be isomorphic to G of P1 direct product etc. G of PR. Okay. So whatever we promised in the last lecture that from Solo's theorem we got exactly this kind of product. So we have reproved it using just simply Cauchy's theorem. Okay. So now what is the upshot so far? So if we have G, let us say the cardinality of G is n, which is E product of these primes P1, E1 etc. PR, ER. So this is the prime factorization. Okay. So now given P which divides the cardinality of G, you define what is called this G of P, which is those x in G such that R of x is some prime P power alpha for some alpha greater than or equal to 0. Then we observed that G is naturally isomorphic to G of P1 cross etc. cross G of PR. So this is what we have proved so far. So any finite abelian group can be written as product of P groups. So that's what it says. So this is called the primary decomposition theorem. Okay, this is called primary decomposition theorem. So, which asserts G can be written as direct product of P groups. Okay. So, now what we are going to do, we are going to only focus on P group. Okay. P group means a group that has some prime power P. So, now once you assume that your group is having prime power P power E. So, then if we prove that if we prove the structure theorem for this kind of groups, then we are done, because any group can be written as product of these P groups, and the given P group is if it is product of a cyclic group of order prime powers. Okay. So, then putting them together we get that any finite abelian group is product of cyclic groups of a prime order. Okay. So, how one can prove this? So, here is the baby version of the theorem. So, if G is P power E and obviously G is given to be finite abelian, so then we claim that G is isomorphic to Z modulo some P power beta 1 Z cross etc. cross Z modulo P power beta R Z, where you can choose the exponents so that you can write it in the increasing order, and this is a partition of this E. Okay. So, with this condition, so this is also uniquely determined. So, moreover, this tuple beta 1 etc. beta R or the partition, so which is denoted by like this, partition of E is uniquely determined by G. Okay. So, we have such exponents beta 1 etc. beta R which form a partition of E, and this partition is uniquely determined by G. That is what it says. So, from this it is immediate that G can be written as product of cyclic groups of prime power orders. Okay. So, and we will also actually verify the uniqueness on the way. Okay. So, we want to actually prove this, but if you think about it, so what this theorem immediately implies. Okay. For example, this actually tells something about these exponents. Okay. So, we need to actually tell you how to pick these exponents beta 1 etc. beta R. So, otherwise we will not be able to actually proceed further. Na? So, but if you think about it, these beta i's, they have some very important property. For example, how the beta 1 chosen. So, let us think about it. So, the beta 1, okay, so this is the highest power of P that appear here. Okay. So, that means, so this is a cyclic group, this is Z modulo P power beta 1 Z. So, if you take the cyclic generator of that, so then the order of that cyclic generator is going to be P power beta 1. But if you think about it, if you take any element of G, okay, so if you take any element of G, because that can be written as some x1 etc. xr, okay. So, any element x in G, assuming that this is isomorphic to Z modulo P power beta 1 Z cross etc. cross Z modulo P power beta R Z. Okay. So, you can see that this x can be written as x1 etc. xr. So, now what will be the order? The order of this is going to be LCM of order of x1 etc. order of xr. Okay, at least the order of x must divide this. Okay, one can check because the orders of p powers, you can check that this is going to be the case. So that means, so at least for sure this order of x will divide this LCM. Now from this you can see that this has to divide the p power beta 1. Okay. So that means any element of G whose order, okay, order of any element of that, order of any element of G must divide this p power beta 1. So you choose this beta 1 such that, so that is the highest possible order of any element of G. Okay, that means p beta 1 is nothing but maximum of order of G where G in G. So this is what called exponent of G. So this is called exponent of G, and exponent of G can be defined for any finite abelian groups, no issue, because we have only finitely many elements. You look at all possible orders of that and then take maximum. So then you can see that this p power beta 1 is exactly captured by this exponent of G. So that is how you capture this beta 1. Then how do you capture beta 2 and so on, we will see over the proof. Okay. So you have to look at PG and then try to do it. But we can see that this exponent naturally appears. So let us make some comment about the exponent. Okay. I will actually prove a very simple lemma about the exponent. So here is the proof. So this is actually true for any finite abelian groups. Okay. So let G be a finite abelian group. Okay. So G is finite abelian group. So then we can define what is called this M, which is also called exponent of G. So this is going to be the maximum order of elements of G possible. So this max of order of G where G comes from capital G. So then what one can prove, so order of X divides this M for all X in G. Okay, once you define this exponent, then the order of any element of G must divide the exponent of G. So what is the proof? So the proof is very simple. So let X in G such that order of X, let us say, does not divide M. Okay, we will get the contradiction. So choose A in G such that order of A equal to M, because this is maximum among finitely many. So it is attained. So you choose A in G such that order of A is M. So now you have this order of X does not divide M. So that means there exists a prime divisor P of order of X such that P power R will divide order of X, but P power R cannot divide M. So that means some power of P divides M, but the power S should be strictly less than R. Okay. So you can choose a prime P which divides R of X, but not, so the some power of that P does not divide, the correct power of that does not divide M. So you call like P power R divides R of X, P power S divides M. So you can choose such a way that S is less than R. So now if you look at the order of this A power PS, so what is this? This is going to be order of A divided by the GCD of order of A comma P power S. So this is going to be order of A is M, and since P power S divides M, so the GCD between them is P power S. So, this is exactly m divided by p power s. Similarly, the order of x power, okay, order of x divided by p power r is going to be just p power r, because this is going to be order of x divided by again GCD of order of x comma p power r. So, sorry, order of x divided by p power r. So, that is going to be just order of x divided by order of x divided by p power r, which is p power r. Okay. So, now you can see that p power r and this m divided by p power s. So, they must be relatively prime, because p power s is the highest power that divides m. So, this must be relatively prime. So, that means you have this elements x power order of x divided by p power r and this another element a p power s. Okay. So, both are actually commuting elements and both the orders they are relatively prime. So, then the order of this is going to be order of a power p power s and order of x power order of x divided by p power r. So, which is going to be exactly equal to m divided by p power s times p power r. So, which is going to be m times p power r minus s. But we have assumed r is greater than s, that implies r minus s is greater than or equal to 1. So, that means this m times p power r minus s is strictly greater than m. So, we have produced one element inside G whose order is more than m, but that is a contradiction because m is the maximum order possible. So, that is called exponent of G. Okay. So, you can't have something else that can be actually crosses this order. So, that proves that this m has this property that order of x divides m, which is exponent of G for all x in G. Okay. So, now using this we will be able to pick our beta 1 when you apply it for finite abelian P group. Okay. So, I will actually continue the proof in the next class. So, we need to actually just say how to pick this beta 1, beta 2 etc. beta r. So, indeed we will use induction and then say that more or less how we are choosing beta 1 is the same way we choose beta 2 and so on in the somewhat smaller group. Okay. That way we will be able to choose this partition beta 1 etc. beta r such that G is isomorphic to this Z modulo p power beta 1 Z etc. direct product etc. Z modulo p power beta r. So, I will complete the proof in the next class. I will stop here.